So no. The last time we discussed block diagram models. Can somebody remind me what a block diagram is? Why do we need it? No idea? So we need block diagrams to study the system. Sometimes systems can get complicated and they have multiple variables and you have different systems within systems. So with block diagrams models, you can simplify the analysis and come up with let's say one transfer function that captures the input-output relationship of the entire system. Nothing is showing. Surprising. Let me reshare the screen then. How about now?
Yes, doctor.
Okay, good. All right. This is what we talked about last time. So block diagram is a pictorial representation of a system. It shows different components, subsystems that make a system and shows their interactions. Each rectangular block represents a subsystem with an input and an output. So as an input to that block is an arrow, and the output of that block is also another arrow going out of it. So if we take this example, we have a transmitter, a communication channel, and receiver. So for this is a communication system. If I want to relate the input signal to the output signal, I don't have an immediate relationship, but I have these different blocks. So if I can combine them somehow, we can know exactly what is the system model or what is the input-output relationship. So it is used to represent a linear relationship between input and an output of a subsystem. So if we let the input and output, so let the input be U, let the output be Y. Okay? Now, with that, the relationship between U and Y is represented by a rectangular block having a transfer function G. So again, what is a transfer function? It's the Laplace transform of the output over the input. So in this case, G is Y of S over U of S. This is G of S. Now in block diagram notation, we have transfer function block. So you multiply the input to it by the transfer function, whatever that block contains, and you get V. We have also the summation nodes. So the output here is V minus W because we have a negative sign here. And we also have what's called a pickoff point. So whatever comes out of the pickoff point is the same variable that was the row that it's coming from. Okay? So with that, we said there is a voltage divider example. This is a static circuit. So because you don't have dynamics, then you can get the transfer function for it. If you have dynamics, then you need to go to the Laplace, you need to go to the frequency domain to get the transfer function. You cannot work on the time domain. So we talked about multi-input, multi-output systems. And we talked about some properties. For example, you have the multiplication, blocks in series, parallel, addition, you have feedback rule. And we also showed this mathematically. And then we discussed moving at some point and the pickoff point. And we stopped here, I believe. So we said that this is an example. So a pressure measurement system consisting of a pressure sensor with gains 1 and also signal conditioner will gain 20. So the block containing the 2 here is just a block with value 2. That's 2 MA over PA. So this captures the relationship between V and P. So V is 2P. So what is the transfer function of this system? Simply this guy containing the 3 blocks. And in this case, you just multiply because it's a cascade, blocks in series, so it's GHK. I have an input here and output Y, then this is the relationship between them. Now we have some rules. So for example, if you have something like this with 2 arrows, one to the right, one to the left, then you can have a different representation of it as 2 different lines. This is just to say that if you have a pickup point, or let's say a point of divergence between a point, this one, then you can represent them by one line, 2 lines, so you have some room here. It's the same system really. In the end of the day, you have the same value going L and K. So if you have 2 pickup points from the same arrow coming out of the same arrow, then it gives you the same value. And one goes to K and one goes to L. So there is no contradictions over here. So can you calculate the transfer function for the following subsystem? Let me give you a small exercise. So this is the feedback rule. The feedback rule is the forward path gain over 1 plus forward path gain. Let me call no, not use the same image. So let me use F here. This is feed F. This is for the feedback system, feedback loop. So you have GH and K. Can you tell me quickly what is the corresponding transfer function representing this system? If you can't tell me that you don't know, or you can tell me what it is. So it is GH over 1 plus GHK. Let me go back to the if I have a feedback system like this, some G over back A. The summation positive, then it's G over 1 minus GH. Then it's G over 1 plus. This is for a general feedback loop. Now we have this feedback loop, so we have first to combine G with H. So this is GH, and then we can let me just erase this, maybe use a pen. Right, so this is one block. So then what is the feedback rule? It's the forward gain P. So it's a GH over, this is a negative feedback, so it's 1 plus forward gain, again is G multiplied by the feedback gain. So it's GH over 1 plus GHK. This is one block that is equivalent to this entire. Here if it's U, and the output here if it's Y, then we have U going to this going to this block. Then you have Y coming out of this block. That's it. It's pretty straightforward. So Abdul Wahab, do you now know how to? Good. All right. So let's study this example. So you can see with systems with different subsystems, things can get complicated. But we've been mainly interested on if I have an input signal, a reference signal, and I am measuring some output. What I care about is what is this output corresponding to this input, right? And in that case, if I have a lot of subsystems, with block diagram reduction, we can represent these complicated relationships to one block. So the question here is, what is that block? Any suggestions for things to do? So divide by nodes. I mean, we reduce them step by step. Exactly. So you have multiple things to do here, and there are multiple ways to do this, right? The first thing that we might consider is maybe splitting this into two parts, right? So let's say we have something here, and we have, let's say, another line here, right? So this is step one. So you can add D with E, then you have one block representing D and E. So you have D plus E as one block. Then you have this feedback loop, which is AB over 1 plus ABC. Then you will have, so you will have two blocks here now, one for representing D plus E, the other one with the feedback. And you'll have these two as cascades, so you multiply them. You have another feedback with F. So this is one way, or you can start with the feedback from F and then do something about it. There are multiple ways to do this, really. So let's step-by-step approach. So instead of me writing them here, I have them in the slide, so we'll go through them one by one. So the first step, as I just mentioned, you can separate this into two lines. They have parallel paths D and E. So this is just one block D plus E. And you'll have a feedback loop replaced by AB over 1 minus ABC. Actually, this is not a negative feedback, positive feedback. So you have minus sign over here. And you have F as a feedback. Then you have a feedback system, right? So these two are equivalent to AB multiplied by D plus E divided by 1 minus ABC. So we have one block here representing AB, D plus E over 1 minus ABC. And we have F feedback to the system. So this is a feedback, this is the path gain now, and this is the feedback. So the resulting one is the path gain over 1 plus, because I have a negative sign here, F the path gain. So let me recalculate this over here real quick. So what is the path gain? It is AB D plus E over 1 minus ABC whole plus, because I have a negative sign here. Same thing, this guy multiplied by F. So it is A B D plus E multiplied by F. Let me use a different color for F. Just to elaborate on the difference between the two. And we go back to the same denominator, 1 minus ABC. Multiply the numerator and the denominator by 1 minus ABC. This is equivalent to, let me use a different color here. Let me use black. So we will have AB D plus E over 1 minus ABC plus whatever we had here. So I'll use this. So it is AB F multiplied by D plus E. Is the same as that. Any questions? All right, there is an alternative. Again, I mentioned that there is no unique way of doing this. So one alternative approach is, after you do the serial combination here, D plus E, you have a pick point here. So you can just move it to over here. And when you do a pickup point and move it after the block, then you divide by D plus E. Right? So you have a feedback of C multiplied by 1 over D plus E. Right? So what you can do is, actually, you notice that you have feedback here minus F, and you have here plus C plus C over D plus E. So these two, there's a summation node here. There is two. I mean, it's the same as one summation node. So again, you have one feedback to the system, which is C over D plus E minus F. So again, here's what we did. So the other way is, you do this parallel combination and then you move the pickup point over here. You'll have feedback paths. One with gain C over D plus E, the other one with F. You have a minus sign here, you have a positive sign. So this is again a parallel combination between F and C over D plus E. Because we have a negative sign here, we can replace this by one block of C over D plus E minus F. And here we have one path gain. So we can use the feedback formula, which will give you AB D plus E 1 plus the same path gain over the feedback. So let me call this P. Let me call this H. Then what we get is P over 1 plus, see, this is 1 minus because it's we have a sign here. 1 minus PH. You substitute that, you will get this guy. Any questions? All right. So let me give you a small exercise. So I'll give you 4 minutes. And while you try this, let me know if you have any questions or if you need if we need a reminder for a rule that we use. Okay? So I'll give you, please work on this exercise. Then we will discuss We have one candidate solution gm over 1 minus gh plus k. Okay, how do you find that? Abdullah, can you tell us how you got this result? Okay, Faisal got the same result as Abdullah. Okay, can one of you tell me how you got this result? Yes, Faisal, please.
So doctor, we have G and H, we take it as first. So we'll have them as in a feedback system. Then the results will be in series with M.
Okay.
And the result of feedback system GH and M will be in parallel with K.
Okay. There is one slight issue here. Notice that this is after the summation node. So once you have one block, not sure that you a parallel combination, right? Where else do you get this K? See what I'm trying to say? So is there a way? How about we move point? And then we whatever result that we. So do you agree with what? Is there any questions about what I just mentioned? Okay, so let's, which seems problematic to here. And what we have is, as we move it to here, then we need to, you move a pickup point to a block. So you need to do uh, by the block, right? So we will have something like this. K over G with summation, and we will not have this guy. Voice is lagging. Is it better now?
Yeah, now it's better, but I
Okay.
couldn't hear what you said earlier. Yeah.
Okay, so what I said is that to come up to compensate for the issue, we are moving this pickup point here, replacing that pickup point which is at a problematic location with something after G. So after you move a pickup point to after a block, you have to divide by the same block value. So we get G, we get K over G, right? And then, is it clear what I just did? What I just did? Yeah, and then what we can do is we can deal with this feedback, and then we can do this parallel combination and cascade them, and we will get the result, right? So you deal with this feedback, so you will have G over 1 plus GH. So this is what the system will look like. You have this block representing this feedback, then you will have another block representing this parallel combination. So in this case, it is K over G plus m. This is y, right? Then you multiply the two in order to get the corresponding transfer function. You multiply these two together, and you get the corresponding transfer function. Yes, Faisal.
Doctor, we divided by G because the node is just behind G, right?
Yeah, so let me go back to the slide where we have the rule for moving a pickup point to after a node, right? So if you have a pickup point here, I think, do we have it in this? Okay. It in the here, yeah. So here we're moving it to before. Let me see where's the one where we add. Mm, yeah. So we have a pickup point here before some G, and we want to move it after G, so we have to divide by G. This is the rule we just used. Does it make sense? Yeah. And then we had a parallel combination with some feedback, and then we had serial combination between the two. We have to multiply and rearrange the terms in order to get a fraction. Now let's have another fun exercise. Can you guys do this one? Should you get maybe, let's say, 3 minutes to solve it? 3 minutes to work through. Any answers? Any answers يا شباب؟ We have ABD plus 1 over 1 plus ABC plus ABCE plus ABCDE. How do you get that, Hassan? And how do you get that answer? All right. So you don't like your answer. That's fine. Made a mistake. Okay. So there is actually multiple ways to do this, right? One idea is to move after D, divide by D. And then what you will have is the following. You will have if you move this pickoff point to after D, you will to this will be E over D. And this one, the third one, F are all parallel to each other, so you can summon. Then you will have one feedback with 3 blocks in series for the. So you can apply the feedback loop. The other way is to consider this feedback loop. And once you're done with it, you have a bigger feedback. And once you're done with it, then you will have the entire thing in series with D. So you'll have a multiplication between the two. And then once you're done with that, you have a feedback with F. So there are multiple ways to do them, but the answer will be the same. The final answer should be the same function. So let's say we do the feedback idea. You multiply B with A, and then you have feedback with C. So you have multiplied B with A, and you have feedback with C. So you get AB over 1 plus ABC. Then you have feedback with E. So you will get ABE over 1 plus ABC. Everything is divided by 1 plus E, whatever we have here. So actually, before you do this feedback, you can also do the moving the pickoff point. So you will get the same answer. So you can still move this pickoff point. Okay, first I have an answer. It is AB over 1 plus ABC multiplied by D. It's hard for me to verify this, but you can maybe, we will walk through the example, so we will you can verify your answer, and if there is something that doesn't match, let us know so that we can discuss what went wrong. All right. So now there is 2 ways to do this, the next step. One way is to move this pickoff point to after D and then divide E by D, and you treat this as feedback. Or you do the feedback here, and then you do a serial combination with D. It's the same thing. You will get the same result. It's up to you how you want to go about it. So now, let's say we move the pickoff point to after D. So if you do that, you have to divide by D. So we have E over D in parallel with F, so it will be E over D minus F. This is the feedback, and this is the gain. So you have A over D minus F, and this is the gain, and then you do the feedback formula. This is what you get. You will have D over B, DAB over 1 plus ABC over 1 minus blah 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 divided by 1 plus ABC. So these might look a little bit ugly, but the idea is easy. The idea is just to apply simple rules with simple steps in order to get one transfer function representing everything we care about for this system. You guys want to do this example on your own? Verify your answer. You want again? Is it clear? Do you have any questions? Let me know what you think. Okay, if you did it and you did not get this answer, what was wrong in your calculations? Share that information with us, please. Okay, if there are no questions, then we will move to the next topic. Before we do that, we have some keywords to refresh ourselves about. We have what's called the summation point. We have the pickoff point. We have transfer function, cascade combination, parallel combination, feedback combination, block diagram reduction. If you don't know the meaning of any of these keywords, then let me know immediately so we can go through it, because these are important keywords and concepts that we care about in this course. Yes, Faisal.
Doctor, is there any certain rules to say that these two blocks are not in parallel or they are in parallel? Do they have, must they have the same node, for example, or stuff like this? Or 'cause I'm facing some problems with it.
If they are in parallel, then they have the same pickoff point, and they land into the same summation point. For example, here, we're going from the same pickoff point. I mean, you might have, let's say, a different node here, but if you have two summations next to each other, you can replace it by one summation. Any other questions? Okay. If there are no more questions, then what we will do is move to the next topic. So let's take maybe a 2 minutes break, because it's going to be slightly different topic. So let's start fresh after 2 minutes. I was not planning to do a revision, Muhammad, before the lab class, but if you have questions, you can ask me after class. So there is an alternative to block diagram reduction, which is signal flow graphs. The idea is similar to block in the sense that we have a pictorial representation of a system, and it helps us the input-output relationship if you have multiple subsystems. So it's a similar idea, but it's a different that kind of simplification of the analysis. So as an outline, we'll talk about the basic elements of a signal flow graph, some basic properties, definitions, and what's called Mason theory, and some examples. So with signal flow graphs, so this is a block diagram, as you see. As you see here, we have multiple ways of capturing the input-output relationships, but essentially every transfer function is represented by a block, and you have summation nodes, pickoff points, feedback loops, and etc. And these arrows representing what goes here, what goes there. If I replace this by a signal flow graph, things can get easier in the sense that from like if you have a lot of blocks, you can have a system that looks maybe slightly better. So if I replace this with a signal flow graph, this is what happens. Now, every arrow represents a transfer function. It's no longer just the input output, and every node represents the node connecting two things together. For example, so we have a block here, right? And we have a variable here, R, right? So every node represents a variable. So instead of having this block representing the input-output relationship, what we do is have some line representing that that transfer function. So it is slightly easier to deal with that sometimes. Maybe you don't like this one, maybe you will like the block diagrams. It's really two different ways getting you the same kind of result. But essentially, this is another method that is popular and we want you to learn in this course. So block diagram reduction can be cumbersome, and we have some alternative, which is signal flow graphs. So let's define the terms. So the signal flow graph consists of branches and nodes. Every variable is represented by a node, and every branch represents a transfer function. So branches represent transfer functions, that if I have a node here, Vf of s, and I have an output node here, theta of s, then G of s is the transfer function. So theta of s is G of s multiplied by V of s. It's frozen again?
Doctor, yes, you can see anything.
Yeah. Okay. How about now? Do you hear me well, Tayyip? Okay. So we have branches representing blocks, replacing blocks. Each branch is a transfer function. And you have nodes for the inputs and the outputs. So this signal flow graph is simply theta of s, which is the output, being equal to G, the transfer function between theta and V, multiplied by the input Vf of s. So we have what's called the source node, where the signal flow starts, which is the input to the system, and the sink node, which is where the signal flow terminates, which is the output to the system. So a node is used to represent a variable. A source node is the input node. All branches connected to the source node are leaving that node because it's the input, so everything is going out of that source node. Input signal is not affected by other signals. We have what's called the sink node. The sync node, we have all the branches connected to that node are entering the node, and our signal is not affecting other signals. So speaking of the relationship, so you have the input, which is the source node U, and you have the output V, or call it Z, which is the sync node. The gain, if I don't have a gain represented here, if there is no transfer function shown, then the gain is 1. The transfer function is 1. So now let's capture the relationships here. So if I have the variable here x, what is it equal to? It is equal to AU, because I have A as a transfer function multiplied by the input, plus Y, right? Because Y is the variable it's directly connected to. What is Y? Y is equal to BX. So what is Z? So you look at the branches connected to it, coming in that, and for each branch you multiply that value of the corresponding transfer function to the branch with the previous node it's coming out to. So it is equal to dx plus cy. So I don't care what happens before y. I just have y and multiply it by c. Y inherently takes care of whatever is before that. Okay? The output variable is just z, which is equal to z. Why? Because this branch does not have a gain other than 1. So if it's the default value is 1 unless we put some other transfer function there. Is it clear? Any questions? Yes, Faisal.
Doctor, but in X, why didn't we include D and Z since they have like a branch?
For x, why is it AU plus y only?
Yes, why not? We didn't include Z.
Because, okay, because the branch is coming out of x. It's not coming to x. You have the branches going to x. The direction matters. You see that? Okay. So here are the terminologies. We say a path, which is a branch or continuous sequence of branches that can be traversed from one node to another. So what is the path from U to V? We have two paths. We have the path going straight, it's as a straight line ABC. The other path is 3 multiplied by H multiplied by 1. So these are the paths between U, from U to Z. We have ABC. We have U. We have 3 H, and you have also W in between. Then we have what's called the forward path, which is the path from a sink. It's a forward path. And we have a path gain, which is the product of gains of the branches that make the path. So the path gains here are ABC, and the path gains here are 3H. This is the path gain. So I multiply the transfer functions. I don't multiply the values between, which are represented by nodes. We have what's called a loop. A loop is a closed path that originates and terminates at the same node, and along the path, no node is met twice. So in this case, we have two loops, right? We have this loop, we have this other loop. So you start at y, and you come back to y. And we have what's called non-touching loops, and we will see why we need them later. Two loops are said to be non-touching if they do not have a common node. These two loops are touching because they have y in between. However, if I have another loop here, then I will say that the two red loops are not touching. This guy and this guy. This loop is non-touching with this loop is non-touching with the other loop. But this guy is touching all of the two loops because you have Y here, you have Z here, which is a common node between the two loops. Any questions about the terminology? I think that's not clear so far about signal flow graphs. Okay. So we're going. So this is what's called the Mason's formula. It is used to capture the linear dependence Tij between the input variable, the source node xi, and the output variable xj, the sink node. So this represents the transfer function of the signal flow graph. Tij is equal to the summation of some Pijk over k multiplied by delta ijk over some delta. And we will explain each term, what it means, and how to get it. But just for any signal flow graph, if you represent a system by signal flow graph, you can use this formula and get the unique transfer function of the system. And again, signal flow graphs are similar to block diagrams in this. They are both pictorial representation of the system. So if you also represent the same system by a block diagram and do the reduction, you will get the same transfer function that is provided by the Mason's formula. So Pijk is the gain of the kth path going from I to j. Delta is the determinant of the graph. Every graph has a determinant, and we will compute it and tell you how to get it. And for every path, there is what's called a cofactor. So what you do is from I to j, what you do is you see how many paths you have. If you have two paths, then this summation will have k equal to 1 and k equal to 2. For every path, you have a gain, Pijk, and you have a cofactor. You sum everything and divide by the determinant of the entire graph. And we will talk about what is the determinant or what is the cofactor, and we mentioned what is the path gain, but we will go through it again. So in this case, we have two paths going from U to V. The green one, which is 3H1, and the brown, which is ABC, and the last segment between Z and V. So what are the path gains from U to V? We have PUV1, the first path is ABC, and the second path is 3H. Now, what is the determinant system? The determinant of the system is something we can compute as follows. It is 1 minus the sum of all different loop gains plus the sum of the gain products of all combinations of two non-touching loops minus the sum of gain products of all combinations of three non-touching loops. And we will have examples to elaborate more on this. But the message here is the following, that you have one determinant for the entire graph, and you can easily compute the path gains going from one node to another. So the only thing left to you to use Mason's formula is really just to get the cofactor, which is also easy to compute. And once you do that, you know the transfer function of any signal flow graph. The cofactor delta ijk is the determinant with the loops touching the kth path removed. So if you know how to get the determinant, then it's easier to get the cofactor. And that's it. So if we go back to the same example, so what are the number of forward paths from U to V? We have two. We have this path that I'm plotting now, and the other path is just the straight line from here to until you reach a V. So you have two. What are the path gains? The first one is ABC, the second one is 3H. You multiply the corresponding branches values, and that's it. What are the loops? We have two loops. We have B and you have CK. What is the determinant of the system? We can apply the formula and get it. What are the cofactors? Again, we can apply the simplified version of the formula and get it. And then we can get the transfer function by just using this information. So the number of paths, again, are 2. The path gains are ABC and 3H. The loop gains are, the first one is B, the second one is CK, and this is the transfer function. Now let's compute. So let's go through the computations of the determinant. The computation of the determinant is as follows. If I go back to the formula, it is 1 minus the sum of all different loop gains, and then we will go to the next items in a bit. We will discuss them. So this is the determinant. It is 1 minus the sum of all the loop we have here. The first loop gain is B. The second loop gain is CK, right? This is the other loop. This is CK, it's not C. Let me erase this real quick. It is CK. Then what is the third term? It says the sum of all gain products, combination of two non-loops. Actually, for example, they are touching loops, so we don't have any non-touching loops. And then we can stop because all of the remaining terms refer to the non-touching loops. Now, this is delta. Okay. So this is the determinant. It is minus B minus CK. I go back to Mason's formula, the determinant. Then what else do we need? We need the path gain of K path and the cofactor. So what is the cofactor? The cofactor again is the determinant with the loops touching the K path being removed. Okay. So for the first path, we have the path gain ABC. Now, if I have the determinant, if I have the cofactor of this path, it's the determinant after removing the touching gains, the gains of the touching loops. In this case, both of them are touching, so I have to multiply by 1 here. What about the second path? The second path is the gain is 3H. I do the same thing, but notice that here I have only one touching loop, the other one is non-touching. So I remove what? It tells me that the determinant with the loops touching the kth path removed. So it is the same as the determinant, but this path is touching the CK loop. So I have to remove the CK part of the determinant, and the cofactor is 1 minus B. And this is the transfer function of the system. And you will see that it's exactly this expression. Questions? Please respond to the poll. Okay. Please, if something is not clear, let me know immediately so we can go through. This is an important part of, I mean, for this topic, this is pretty much the most critical point, the most critical idea, the Mason's formula and how to compute it and what are the components of it and how do you get them? How do you get them? So if there are no questions, I will keep going forward, but at the same time, we will cover more contents and you might be bombarded. So if something is not clear, please let me know. Otherwise, I'll assume it's clear and keep going. Okay. So if I remove my computations, again, you'll see that we had one path, two paths. These are the two paths from U to V. And we can have another example here, right? So let me look at this example. But next time we will start with this example, starting from R. We're terminating at Y, and we want to use Mason's formula. So we have two forward paths going from R to Y with for loops, and how to relate R to Y is through the Mason's formula, which we will discuss next time. With that, I will conclude. So inshallah, next time we will do this example, and we will have the second in class